This is Keshava Munegowda from Nexus Instruments, Bangalore, India. So I'll be presenting on power fails of fact file system. So fact file system, which I've been working on almost since 5 years, more than 5 years. So earlier I was developing this file system for nucleus operating systems, and we did a couple of innovations in the nucleus. So now I'm into the Linux. So I'm proposing some of the things which we can open source. So the fact file system is just pretty old file system, but unfortunately it's still existing in most of the embedded storage small devices. So what we are doing in this is a design of making a power fail-safe fact, okay, which is the fact specification compatibility. That means works with Windows or Linux PC, and defining the logging and how the recovery has to be done in case of power fail. So this is the agenda. So in one slide, I'll just go through what is actually the fact file system. It's just a logical organization, and why we need a power fail-safe, and the state of art, just to indicate overall done what with respect to making a fact as a power fail-safe. In that, we will be covering a couple of file systems called TFAT, KFAT, RFS, TFS4. So these are some of the things for Microsoft and Samsung. And we will be defining the what is TAL fact log-based fact file system, and which defines some of the mechanisms called the directory entry logging, fact entry logging, and we will be defining an element, a building block of this power fail-safe mechanism called a log record. And we're going to see almost all the file system APIs, like how we go to make it as a power fail-safe. That's one thing, and we'll end it up with references. Okay, so that's about the agenda. And finally, of course, we will have a Q&A sessions. And most probably, is there anybody from Texera? I saw they were in the part of this ELC. Okay, so let's start. This is the logical organization of the fact file system. So we can see any storage as just a linear blocks, linear array of blocks, storage blocks. So a block can be a one element, I would say 512 bytes. And in a first block, typically we'll have a BPB, BIOS parameter block. So we typically call this as a boot sector 2. So what it contains is the information about the disk, like how many blocks you have, total number of blocks, and the information about the fact file system. The fact file system defines another concept, or what I would say is word is a cluster. So cluster is nothing but either one block or a group of blocks. So block and sectors are same. So I'll be using them interchangeably. Okay. So this BPB will define total number of blocks, how many fact tables you have. So how many sectors per clusters, means numbers per one cluster, how many sectors you will have per cluster. So that is particularly cluster you need particularly to address larger size of the disk. And apart from that, how many sectors, how many blocks you need it for fact. This fact2 is a backup of fact1. So what is this fact contains is typically file is stored in a form of linked list of data blocks or clusters. The linking happens, okay, in fact table. That is called file allocation table. So you can see that in the bottom of the slide, file1.txt, which has a starting cluster number 3, and the starting cluster number 3 to next cluster 7, and then the end of the file. So that linking mechanism happens in file allocation table. And fact2, it is meant for, especially, it has a historical reason, and it was for the magnetic kind of tape kind of devices, where one fact is, but sectors of one fact is not working, then you can recover the same thing by fact2. That was the reason. And fact2 is just a backup of fact. So that's all about the files, just an overview of the fact file system. So what is the need of power fail-safe FAT? In case of any uncontrolled power loss or something like unintentional device disconnect, we would end up in a state where metadata is corrupted. Metadata means data or something like a data structure of the file system which properly represents the files or directories. What happens is, suppose you are appending a file or creating a file, okay, while making these links, power goes off. That's a one case. Or something like you are creating a new file or a new directory and power goes off. That's the second case in a directory. So in those two situations, what will happen is, it will end up having the orphan data clusters. Means data clusters are written, they are indicated that allocated in a file allocation table, but none of the files are pointing to that. Okay. So typically that will eat up the usage area of the file system and will end up in formatting the file system. So apart from that, in the second case, what it can happen is, you will see a lot of junk files or directory gets corrupted. Once users see such kind of data, I don't think the data will be trustworthy. So particularly in these two use cases, or in these two situations, we need to make sure that file system is always consistent and the operations are atomic. Either it happens or it doesn't happen. Okay. So state of art have been some of the file systems existing today, but haven't seen none of the file systems which have been open sourced with power fail-safe mechanism with FAT. So the first one is TFAT. It is again by Microsoft. Of course, FAT is by Microsoft. So this TFAT, call it as a transaction-safe FAT file system. We'll briefly see how we achieve the power fail-safe. Another one is the KFAT. It's a log-based transactional FAT file system. This I've seen from US Korean conference in 2005. This was the first presented as a paper. And the robust FAT file system is again by Samsung. And TFS4 transactional file system version 4. This is, he claims that it's particularly for performance optimized for one and flash memories. So in a TFAT, as I mentioned earlier by Microsoft, and this is for the WinC operating system. So first available with the WinC 6.0. So how it makes it is, suppose you are creating a file, new file, or deleting a file, or updating a file, any file operations you are doing, or directory operations you are doing. So it requires a data cluster update. So in this example, file1.txt. Okay, so suppose if I am updating a cluster 7, what I do is, instead of directly updating, so I take a new cluster, cluster 9, and then copy cluster 7 plus updated data, and then I create a link. Still, if you lose a power in between while making a link from cluster 3 to 9 and 9 to 18, it's again a corruption, a system corruption. So for that, what he does is, he makes FAT2 as a working file allocation table. FAT1 as always a good FAT, means a committed FAT. So first he makes the changes in FAT2 and then he copies in a commit point. So commit point, what TFAT defines it, it could be in a file system initialization time, or it could be something like a timer based, it could be anything. So he copies entire FAT2 to FAT1. That's a mechanism. So this achieves a transaction safe, as I mentioned. The problem with this file system is slower performance. The one reason is, allocation of the new clusters, and other one is copying a FAT to complete a file allocation table from FAT2 to FAT1. So in a larger disk, typically if you are supporting several GBs, let's say up to 32 GB, so we'll be having the FAT1, FAT2 into several MBs. So copying the entire thing typically slows down the performance. So this is the mechanism. And next one is the KFAT, RFF and TFS4. Since this is all three are the variants of a common, KFAT is the basic one, and RFS and TFS are built upon KFAT. So what KFAT defines is, you have a FAT1, FAT2, and you create a normal user file, but it's a little bit different. We call it as a log file, which is the first file in the root directory. In any drive, it will be a first file. This will be always a fixed size, so that we don't do any changes in the file. Any metadata of this file will never change. We'll keep that as it is. Only data portion of that file, log file, changes. So in the log file, what do is, we log all the operations before making any changes to the file system. So if you're creating a file, first you log it here. Once you are reached to the stable state, then you commit the whole thing to the file system. So this also definitely achieves our fail-safe. And what I have seen is the paper which I referred it. He claimed there are 13 log types are there, but complete the log types were not given. That's the first thing. And other thing is, since he logs even the even the cluster updates also, typically the FAT entry updates also. So this also takes time. So that's a mechanism. Now what we are doing, what we are proposing is a new thing which combines the good features of these two things. So what TALFAT does is, log-based for fail-safe FAT file system does is, we define a logging phase as well as the committing phase. In a logging phase, we typically update all the entries, file system operation entries happens in FAT2, and in the committing, actual committing happens into FAT1. So it means FAT2 is always as usual the working FAT, and FAT1 is always the good FAT. And we keep the log file. The only difference is, don't log the FAT entries. Log only the directory entry updates. Directory entry updates should be something like a file system name change, the renaming, or something like changing the attribute, or the size of the file system got changed. So these are the things we log only those things to the log file. Whereas once you started adding the clusters, or once you start removing the clusters from a file, don't log such a kind of operation. Instead, write them to the FAT2 and then update them to the FAT1. What it does is, first thing is, your number of entries will be less in this. So definitely your number of committing operations will be less. They will reduce the time. Apart from that, most important one is, we copy only the updated entries from FAT2 to FAT1. It is not an entire FAT table transfer, copying an entire FAT table from FAT2 to FAT1. So that is the objective. In case of logging mechanism, since it always yields extra writes, you will always see a performance degradation. What best we can do is minimize the degradation. So that's the objective of this file system. So we try to improve the performance by minimizing, by not updating the FAT entries into the log file, make directly to the FAT2, and then use that one as a scratch part, and then update them to FAT1, and update log only the directory or the file attribute changes. So this is about the overview of the TALFAT. So here we define a log record. So log record is nothing but a 32-byte entry in a log file. So this 32-byte entry defines what is actually the file system operation. Any file system operation, for example, file creation, renaming, delete, directory creation, renaming or updating a file, any file system operation is defined by either by one log record or multiple log records. So typically in almost all the APIs, what we have seen is you need only 2 log records. That is sufficient to do a fail-safe of all the file system APIs. Okay, so apart from the log file, this TAL-FAT defines a log table too, so which is an option we want to use for the security's purpose. Okay, so we'll see what is actually the log table. Log table nothing but it serves the same purpose of log file, means where you can keep the log records, so logging the file system operation, but not as a form of file. It will be a part of your result sectors. So what is actually the result sector? Result sectors, you can mention it in a BPB or in a boot sector, saying that after this BPB, before starting file allocation table, there could be X number of blocks where I'll be leaving as it is for a vendor specific purpose. None of the Linux implementation or any implementation of the FAT file system implementation which adhering to the FAT specification will not touch these blocks. So you can log all the file system operations in result sectors. The same log records, instead of logging into the log file, you can log it here. What's the advantage? Only one advantage is it will not be in a form of user file. So it will be completely hidden from the end user. That's the advantage. So this you can decide while formatting any disk, like how many result sectors you need. Okay, typically you can, in general I have seen in FAT16 only one result sector, you can extend that, and in FAT32 it will be 36 or 34, or in some systems I have seen 32 result sector. So this is about making a log records in a result sectors. So apart from this, we have another mechanism where we can place the log table, that's called result clusters. Result cluster is nothing but again a cluster, but marked as result. So where do we mark is the state of all the clusters will be marked in as file allocation table. So in the file allocation table, in the particular entries, let's say entry 2, 3, 4 in this diagram, if I mark them as result, then corresponding clusters, cluster 2, 3, 4 are result. So what it indicates is your operating system or the FAT file system of the Windows or Linux or any implementation will not touch these clusters. So this data will be completely hidden from the user. So how do we make that as a result cluster? FAT specification defines a values called 0x FFF6. So this is the value I have to write it to the FAT entries to make the result clusters. What is the advantage? It's the same purpose of the result sectors. Only advantage is whenever you don't want a logging mechanism, let's say one weird case would be something like you have fully packed shell and you want to disable the logging mechanism in any of the embedded gadget. In that way, in that situation, what you can do is you can mark these as free clusters so that these can be used for the data clusters of the files or directory. Whereas in result sectors, which I explained before in this case, you cannot change them back. You cannot move FAT1 to result sectors. You can do it only after the format. So meaning you will be losing the data or you have to take a backup of it. So that's the advantage. This is dynamic, other one is static. So you will have it only once. So this is about the log table. So now, as I told, TAL-FAT defines the two mechanisms. One is the FAT entry logging, other one is the directory entry. FAT entry logging, wherever you make a cluster update, wherever you modify the chain of the data clusters, that's we call it as a FAT entry. Or in this example, let's say I'm extending this file, file1.txt, simple example. I'm adding two more clusters to the file, so that is cluster 9 and 20. What I do is, first I'll not directly write it to the FAT1. First I'll write it to FAT1, FAT2, and then I'll update to FAT1. Here I'll not be updating the complete FAT2 to FAT1. I'll be updating only the updated entries, 19 and 20. So this is about the FAT entry log. So log record. So log record, as I told, this is a 32-byte entry or an element in a log file or log table. So single operation, single file system operations is performed using a single log record or a multiple log record. Okay, so some of the file system operation which needs a single log record is file creation or directory creation with short file names. Short file names in FAT specification, it means only 8 characters of the file name, and .3 means 3 characters of extension. Deletion of the file, updating the file. Let's say you are changing attribute of the file, or actually you are adding few more clusters to the file, or you are truncating the file. So other things is which requires other file system operation which requires multiple log records. Or suppose you are creating a file name of more than 8 characters. It will be typically, let's say, up to 256 characters. So that would typically need you have multiple log records. Apart from that, renaming, file renaming or directory renaming requires multiple log records. So this is the structure of the log record. What kind of information you had to log before doing any file system operation. So in the left hand side, what I am showing is the definition of the FAT32 and directory entry. The people who are familiar with the FAT specification, so I think for them it is easy to understand. What it defines is any file or any directory or a file, it will be a part of file directory only, another directory only. So how the directory stores the file information? That is like this. What it keeps is name, 11 characters, means 8 characters as a primary part, and then extension part is 3 characters, 11 characters file name, and then the attributes, whether it is a directory or a file or a read-only, these are the things. And then the NT reserved bit. This specification says reserved, but I have seen the Windows XP and some of the implementation uses this bit. That will be seeing it later. And the creation time. So this is the millisecond stamp of the file creation time. And then the creation time, creation date, time of was created. Of course, he defines a format, in which format you have to store the date and time of the file created or updated. Okay. And the last access date. In my experience, I have not seen many of the implementation which works on the flash memories. Not update this because it will cause an additional writes. We try to minimize that. That's the first thing. But anyway, it is there. It will get updated. Typically in the host-based machines. And apart from that, you have a file name. What is actually the file attribute, and then what is actually the size. You can see that I think it is incomplete. It's not completely seen. Okay, this is actually 32 byte. I think here you can see that directory file size. So apart from this file, this directory entry will be pointing to where actually the first data is residing. The cluster number where actually the first data is residing, first data block. So starting from first data block, rest of the chain will be represented in file allocation table. So only the first data cluster number will exist in this directory entry. So we are changing this. No, sorry, we are not changing this. Our log records look similar to this. So what we are doing is, the one which I have made it bold is those are the things where I keep the different information. First of all, say, so name of the file, attribute of the file, it will be same, whereas instead of NT reserved bit, I'll keep the LFN count. This LFN count is a log file name count, means how many long file names you have. In case your file name creation is more than 8 characters or 8 letters. Okay, and what is actually the log operation? Is it an update? Is it a file deletion or directory deletion? Or is it a rename? Or is it a creation of the new file or directory? Or if it is 0, say that the different values I'm mentioning here. If it is 0, it means there is no operation for this log record. Instead, the operation specified preceding to this log record, the same operation will be a part of the first log record. So it indicates that it is a second log record, or it's not a first log record. First log record typically defines some operation. Rest of, if you have a succeeding log records, it will not specify any of the operation. It will be kept as 0. And the index, directory cluster. Let's say you are, I'll assume that you are creating a file of 8.3, meaning 8 letters, that the log record is getting created, and it will be a part of some parent directory. So in which cluster you are creating this file? In which cluster you are writing 32-byte directory entry? So that's a cluster name, that's a cluster number, we will be storing it here. And starting from that 0th index, at what index you are creating this directory entry? So that's called a dir index. And in next 2 bytes are the higher word of the first data cluster. In case of FAT32, it will be 32-bit cluster number. So higher word, meaning higher 16-bit number will be specified here. So in the logging mechanism, depending on the logging operation, so I'll be treating this value as a different one. In case of update, meaning whenever I'm updating a file, it means whenever I'm adding a new clusters, there will be already an existing cluster chain and the new chain which I will be forming. So this defines the starting cluster number of the new chain. So where I need to link both the things. Okay, this we'll be looking into once I start explaining how the file write happens, file write as well as file close happens. Okay, so similarly, I'll be using the last word of the first data cluster, that is here dir LST cluster low. That's the one. So that's about the log records. So using 32 bytes, I'll be keeping almost all the information. So what kind of operation it is and the necessary cluster numbers or new data which needs to be updated. Let's say after file update and file size might have changed. I have written some few blocks I have written. So there will be a new file size. So with that, what I'll be having is a log record with the update operation and the new file size. So this directly will get updated during the commit operation. Okay. So this is the log record with long file names. Whenever we create a bigger name file or a directory, so what it happens is, you will first log record will specify that this is a creation, and in the first log record only we specify that how many 32-byte entries you will have followed to this. So what it will have is the 16 Unicode characters. Next subsequent log records will specify the 16 Unicode characters. So suppose more than 8 letters, so it will be definitely 2 log records. Okay, so 3 log records. So where the first log record will contain 16 Unicode characters, and the first one will specify how many LFN entries are there. So this is about the log records with LFN. Whenever we commit, means once we added log record to a log file or a log table, so it will have a proper direct file name. Okay, whenever we commit that, the first letter of a log record will be changed to hexadecimal number 0xE5, meaning saying that either it is committed or discarded. Why are done is typically the FAT file system implementation does the deletion of the file or directory like this. It just updates the first character. So that's how I will be indicating this one as a committed operation. Okay, this is about the what set of operations that typically do in case of any file system API is involved. So what we do is typically I have chosen here assuming that we are doing some file update. Most of the time, 70% of the time, what we do in the gadgets is either we create a video record or copying a data. So most of the times, file write is most of the time what operation we do. So in case of that, assuming that, and it holds good to all the file system operations. So what actually the logging and committing does is, so we see the free clusters in FAT2. The FAT2 gives you the newly allocated, always a working FAT, since you have to see for the allocation of the new clusters, you have to look for a free clusters in FAT2, and then you write a file data or directory data to those clusters, then mark them as allocated. That we call it as logging, and that has to happen only in FAT2. And then create a log record of what kind of operation you are doing. Okay, so typical operation would be, as I said, create, delete, rename, truncate. Okay, so and then that's a logging mechanism. Once we do the committing, so I'll tell you when actually we do the committing. So once we started doing the committing, what we do is read the log record, what is actually the operation, and start performing that. And you will figure it out from which cluster or cluster entry you need to update the entries from FAT2 to FAT1. So that's a FAT1 update we are going to do. Suppose power loss happens during a logging. If the still logging is not exist, so nothing you can do using. So that's all. File system will be still inconsistent. Once the log record is created and it is given to the log file, it means your file system operation is safe now. So after that, while updating to the file system, let's say if you lose power, then definitely, so in the next immediate reboot or while mounting a file system, so you will read out the log record, start committing the uncommitted log records. So this is about the file creation or a directory creation. How do we do? As I said, the logging. So how we do the logging is, first we allocate a cluster. If it is a directory creation, dot and double dot entries. Typically every directory will have dot and double dot entries, just pointing to the current directory and to the parent directory. And in case if you have a log file names, you will be having a multiple log records. So these are, that's the first thing we do in case of file and directory creation. While committing, we'll be updating FAT1 and then the processing the log record. Here that one typical use case would be, whenever we create a file or directory, we'll be having a parent directory. And that parent directory might require addition of new cluster too. Let's say in one cluster I can create some 16 or 32 file names. I can have 32 file names. When I'm creating a 33rd or 17th, depending on the cluster size, you might need one more cluster needs to be added to your parent directory. In such a scenario, we need to create another log record which has to be processed and committed before you create a file or directory. Meaning your parent directory, that's what the directory update operation where I'm showing. should happen whenever your parent directory requires additional data blocks, data clusters. Okay. So apart from that, in case of short file names, the reserved bit, as I already mentioned here, the NT reserved bit, the FAT specification, not the specification, the typical implementation uses some 3 set of values to maintain the lowercase and uppercase letters. Suppose your file name is completely with lowercase, we will define with some of these values. Or if it is completely with uppercase, we need not to have these values. Okay. So these are the values will get calculated while committing a log record. Okay. So this is about it. Whenever we, this already explained in the previous slide itself, whenever I create a new file or directory, it might require update of the parent directory. That's what we do. Search for a new free data cluster in FAT2 and allocate that to the parent directory through a login. Commit that first and then take this operation. So what we, the typical stack kind of implementation, so where that is not the first operation we are going to start. Instead, we push that back, push it and then take this one as a new operation, that the directory entry. Once you process that, then you start create a new file or directory. Okay. File or directory delete operation. This requires one log record saying that which entry you are deleting. Apart from that, typical operation would be something like if I am deleting a file.txt. So what I do is I'll go and search what are all the cluster chain in FAT area. Once I get the complete clusters, allocated clusters, start deleting. So typical implementation by the specification is it goes by a linear fashion. Okay, starting from cluster 3, 7, 9, 18, 27. Suppose the power goes off when you are deleting the cluster and when you are making the clusters as free. Let's say you have made 3 as free and that time power goes off. Starting from 7, 9, 18, 27 till end of the cluster chain, what it can happen is it will remain as orphan clusters, meaning the chain is existing in the FAT but not allocated to any file. So in order to avoid that, simple mechanism is you have to traverse through all the FAT chain, collect all the cluster numbers, keep it in your RAM, and then do it in a reverse way. Start marking, starting from 27, start marking the NSC. Once you free it of the cluster 3, then you mark the log record as committed. That's a delete operation. Okay, so this is delete requires one log record plus reverse cluster deletion. Similarly, the file truncate too. So one log record and you will have reverse cluster deletion till the requested size. So let's say I'm reducing the size of the file, so in which requires some deletion of 2 clusters. In that case, starting from 27, I'll go in reverse fashion. So I'll end it up till 9, and 9th will be, I'll mark it as end of file after 9. Okay. So apart from this is the major operation. Typically, most of the time, what we do is the file write and close. And thus, whenever we write the file, we look for the free clusters in FAT2, allocate them, write the data, file data. Okay, so that's only the FAT2 update. So we will not be updating the FAT1. We are not updating the file size. We are just writing a file data and making a linked list of the data clusters in FAT2. Once the file close is involved, that time we create a log record saying that it's a file update. That file update will have a new size as well as the new cluster chain, so which is existing in FAT2, and that log record will contain the last log cluster also, where the file needs to be updated. So once that is done, 2 clusters will get linked in the committing phase, and that's the end of your file write operation. What it means is, suppose you lose a power during a file write, you don't see the off written file. Something like several MBs you are writing, once the power goes off, you typically come back and see that okay, the file is incompletely written. Even though size and everything is proper, that is not the one. What you do is, typically you delete the file and start copying it again. In this case, you will not figure out that. Okay, so in case of file or directory rename, we typically will have a source and destination from where we are moving the file from one directory location to the another one. Okay, so typically it will have two log records. So one is the source, which specifies from which cluster, which index you need to copy the file name, for data cluster change to the new name, and the second log record will specify the new file name. So the second log record can contain a short file name, multiple log records. If you are extending, suppose di or let's say file1.txt is getting renamed to long file name dot blah 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 blah. So in that case, we'll have multiple log records, where the first log record will say file1.txt has to be renamed, and the second log record will say that okay, there is a destination where you have to commit this log. Yeah. Apart from that, the following the log file names will specify what is actually the new name of the file. So that's it. Okay, so key point here is, except file write, for all other operations, file creation, directory creation, deletion of the file, everything, first we create a log record and then we commit. In case of file write, we do only the FAT2 update, and in case of file close, we create a log record which includes the FAT2 update. Okay. Apart from that, let's say you are reading the disk statistics and you are just simply reading a file, or file opened in a read-only mode. In that case, you don't have anything to log, because that will not change anything, any metadata change in the file system. So that's about my presentation. So I have references here. FAT specification is available by Microsoft, and TFAT we don't have much info. In fact, I digged it out through one of the patent document. KFAT, yes, there is a conference paper. RFS and the mechanism which explains the RFS power of safe mechanism, all those things, and the TFS4 mechanism. So all this available in the Samsung website. So any questions? Please.
That is an open source project, and then RFS is a closed project.
Is it?
Does it open source?
Yeah, I know that it's not a open source project. So since it's not yet available in the open source, I'm just proposing this as one idea that we can push. Yes, sir.
Do you have an open source implementation of this? You don't have?
No, not yet. So okay, I need to tell about the history. In Nucleus, we did this implementation. Using this directory entry logging. It's not completely directory. All logs, we keep it in a reserved clusters. Okay, so that we saw some performance drawback in that. So that's why we are proposing this. Implementation is not yet available, just a design. So anyway, yeah, that's all. I'm leaving my email ID. Please mail to me. People are interested. So I want to take this. Yeah.
My impression is that because you're not taking into account how flash media actually work, this will be neither reliable nor fast if you actually implement this.
Okay.
I have a presentation later today where I talk about how most modern flashes work. So the three problems that I see is you do not take into account the erase block size,
Yeah.
which means that you have problems doing atomic.
The one point is this takes care of only the file system operations. Okay. Underneath, you need a block management.
Right.
I'm still not defining like how do I overwrite.
Right. The problem is that for all the media that this is interesting for, like SD cards and USB sticks, you have no way to influence the garbage collection and the where level.
Yeah, from the file system, especially from FAT file system, definitely, I take this one. Definitely, there is no way to influence the flash blocks.
Right. And the way they implement it, this won't work. Like you can only do atomic writes of like 16 kilobytes. So if you have 32-byte log entries, you'll always overwrite the whole log.
Yeah, I'll be overwriting the whole block every time.
Right.
That's it.
The other thing is you have write disturbance on MLC flash. So updating one block may destroy a completely separate block. And if you want to be reliable, you really need to know which block that is, and you don't have that information.
Sorry, come on, I didn't get.
On MLC flash, it can happen that writing to one block and getting a power fail during that, it destroys another block on the underlying flash.
This is not out of the package anymore. It's a question.
Yeah.
Flash software have to make this work.
But they don't.
That's your
They're not
garbage
reliable.
collector has to take care of it.
I mean, you cannot make it more reliable than what the underlying stuff does unless you know what it's actually doing.
That could be the one more point where we can think of it to explain this idea. But as of now, the fact thinking of what kind of media it is operating, I believe it becomes more and more flash specific. So I want to see this one as more like how do you make atomic file system operation? That's the first thing. Your flash management software should take care how you are going to, how you are reliably write the blocks, one complete block. Even though I update 32 bytes, it will be written as one full block. Of course, what best we can do here to improve the performance is by some of the buffering, and that again includes some of the. Once you start doing the buffering, definitely your accuracy of the power failsafe might come down. I'm done. Okay, thanks a lot. And I thought, okay, I'll get a much bigger forum, but anyway.